if it's a single point charge, perhaps even if it has a constant velocity like so, some place over here is going to experience this particle's magnetic field. But let's just see if you can put a few of these pieces together yourself. If for just a moment I hearken back to the days of electric fields, I would be able to determine the electric field if I know this distance, right? Now, answer me this. If I move point P closer to charge Q, will that increase or decrease the strength of the electric field? Let me say it again, because I want to make sure everybody can answer this question. If I move point P closer to charge Q, will I experience an increase or a decrease in the electric field? All right. So consider position S. Position S is clearly going to experience a larger electric field. That electric field is going to be in a slightly different direction, but definitely much larger. I say slightly different direction because point P and point S aren't along a line that connects them to Q. So the direction of the electric field for S will be like that, and the direction for the electric field for P will be like that. Does that make sense so far? But as long as this arrangement stays, those electric fields will remain the same for all time. Good so far? Now, if I asked you to calculate the electric field, you would just need to know what those two separate distances are. And from there, you could calculate the size of that electric field. Here's why the magnetic field is different. And as you're taking your notes, please actually take them. Listening is nice, but actually take them. The electric field was static. Once established, you could easily figure out what the electric field was everywhere in the space around those particles because it remains constant. Take a minute, get something like that into your notes. Again, once the electric field is established, it's constant. Therefore, you know what the electric field is everywhere in that space. Now, getting rid of this for a moment and going back to considering point P, what's the magnetic field at point P right now? It's got to be 0. Charge Q isn't moving. Now here's the rub. The instant charge Q has a velocity, a magnetic field is created. Now, bear with me. Do you think the magnetic field strength is constant everywhere in space? Or do you think places closer to the charge experience larger magnetic fields and things further away from the charge experience less magnetic field? Which makes the most sense? All right, so we all probably agree that proximity has something to do with the strength of the magnetic field. All right, then here's the problem. Are particles moving? Which means that point P is not experiencing a constant magnetic field, but a magnetic field that is going to be changing all the time. Right? The particle's only here for an instant and is gone. and is moved over to here. Suggesting that whatever we calculate for the magnetic field at point P only existed at the instant the particle is at the first location and then is constantly changing. This is why Biot Savarte is usually not taught for point particles. Because generally, independent particles moving through space are creating a transcendental field. A field that is transient, existing only for a brief moment and then is gone. Because it moves away from that point. In fact, when we try to consider what the shape of this field looks like, consider we look at as the particle moves through space, it's creating a circular magnetic field around it. A magnetic field that's smaller ahead of it, again, proximity, and of course, smaller behind it. So as this particle moves, its magnetic field, again, is very transient, increasing in size as it reaches a point of closest approach, and then reducing in size as it leaves. There is one saving grace here, though, something that is not like electric fields, something that makes this, in some ways, much easier to deal with. If you're in this region of space as the particle passes, that entire region is going to see a magnetic field that's all in the same direction, even if it's all not the same strength. So a magnetic field is going to be increasing in size and then decreasing in size. It will always be downwards into the board here, or downwards into the page. While on the other side, the magnetic field over here, always out. So the one nice thing at least is that, one saving grace is that. But aside from that, and if you're not in the same plane as the motion of the particle, that's not going to be true. But it is a bit of a convenience. Now, to get an idea for what this law looks like and understand that you will not have to actually calculate using this rule, but I think it's impressive for you to be able to discuss it. The rule looks like this, and I'm going to be, I'll be clear with you, there's no other way to write this rule for me to be accurate, so I'll explain why it's written this way, but just so you know, it's not pretty. This is a Biot Savarte law for a point particle moving through space at a specific instant in time, dv. You integrate this based on how the velocity is changing. We won't have to do this, but this is what the rule looks like. Sometimes, just so you know, I'm not going to rewrite it. Sometimes it is rewritten, though, as dq v cross r. This is the way I would prefer to see it, but I've seen the law both ways. This one makes the most sense to me. It assumes like a bar of charge moving through space. So it allows me to integrate across the geometry of the charge. But sometimes it's written as dv, so you can express the geometry of your configuration in terms of dV. It doesn't really matter which one you choose. They are linked together, the charge and the velocity. There are features of this law, though, I want you to know. And if you want to make it simpler on yourself, for those of you who just simple minds, for a point charge, this is it. It's not an integral. For a point charge moving through space, this is what it is. So again, not an integral. You can just do it like that. Now, there's a lot of little pieces here, but first, I really do hope that you see the clear similarities. There's something incredibly elegant about this symmetry in space, which is why I really like to make sure you've seen Biot Savarte for a point charge, because it is elegant. I don't know why space works this way, and nobody really does, but it has to work this way. For whatever reason, this is how it has to work. But the fact that they're both inverse square laws, the fact that they both have some single solitary constant that's related to 4 pi, again, weird. You know, the fact that they both are vectors and they both fall off, you know, at the same rate. There's just some certain amount of elegance there. But the cross product with R does add an intriguing difference. If our point is here, and we wanted to figure out the direction of the magnetic field at point P, I don't want to draw an X there, I'd rather we just assume that point P is inside that box. Determining the direction of the magnetic field can be done using the cross product here. It's V cross R hat. If you don't remember, R hat is a vector that connects the charge to the place in space. It's a unit vector. So although I drew an arrow that's the entire length of R hat is in the direction of R. So I know it's tough, but it's velocity first. And then you move your middle finger to line up with R, and your thumb points in the direction of the magnetic field, which is into the board. Now, it shouldn't surprise you if you place your thumb in the direction of the velocity, your fingers curl in the direction of the magnetic field, the same way it would for a current carrying particle or a current carrying wire, which still puts us into the board. Remember, our goal is to ensure that all of our methods for calculating direction that involve the right-hand rule are consistent. And this too is consistent, so the magnetic field into the board over here. Now, like I said, Biot Savarte, great, but I want you to imagine what this really suggests. If you have all of that information, how fast it's going, how far away it is, and the size of the charge, you can get the magnetic field. It's not that hard to calculate, but it only exists at that moment for an instant. And then all of a sudden it's changed, its location. R is changing, and R, V cross R is never changing here, but R is changing all the time. We know that R is related to V. The only time it's not, and this should flip you out a little bit, if the velocity of the particle is that way, R is related to V in a very known way now, but there's no magnetic field. This particle, Q2, doesn't create a magnetic field in front of it or behind it. And neither of them do. Remember, the way this works is there has to be a cross-product solution. Right now, the angle between V and R is 0. No magnetic field. So particles coming at you don't cast a magnetic field ahead of themselves. They cast it to the side, but not ahead. So if it's going to pass near you, yes, there'll be a magnetic field. But if it's going to strike you, no magnetic field. I'm not sure if that matters. Really? Even the schools locks down once the middle schools all start up, sending our attendance in. It's kind of crazy. All right. Now let's get to the one that you do have to do. This one you have to know, and there's no easy way around this one. This one we're going to be using. In fact, I just was being nice to you. I showed you Ampere's law first. I did that because I hope you all realize Ampere's law to figure out the magnetic field around a current was really easy to use, wasn't it? You guys saw it yesterday. It was just stupid easy. Well, remember when we would do those rules with the when we'd find the electric field from a line of charge, just to realize that Gauss's law made it super easy? Well, we're doing it in the reverse. We know our answer is going to be that the magnetic field from a long line of current, a long cable of current, is going to be mu naught times I over 2 pi r. However, we can find this answer by using the current form of the Biot Savarte law. The current form of the Biot Savarte law has to be written as a differential, because although this cable might have a current passing through it, as you probably can guess, this piece of current right here contributes to a magnetic field over here, just like a single particle would. And this piece of current also contributes to a magnetic field right here. And this piece of current does. You see where this is going, right? That each piece of current along the length of this wire contributes its own amount to the magnetic field at point P. And all of them together combine to form the net magnetic field. So if I wanted to find the magnetic field of this piece of current, which I will call ds, because it's based on the length of the wire, then its contribution to the magnetic field, and this is not going to be a surprise, I dot ds cross r hat over r squared times mu naught over 4 pi. That's Biot Savarte for a current carrying wire. Yep.
So, correct me if I'm wrong, but the mu naught, isn't it just 4 pi times 10?
Yes, I know. I get the irony here. I get the irony, and you don't have to go into it. Yes, mu naught is 4 pi times 10 to the negative 7th. And yes, Biot Savarte divides away the 4 pi. Yes, you're right.
So it's just times 10.
And just sit back and be happy for a moment, because yeah, trust me. And when I say trust me, remember, epsilon naught and mu naught can both be written in terms of C. Wait, let that play in your head for just a minute, because for all the electric field stuff, it's 4 pi epsilon naught, which means every epsilon naught can be written as mu naught and C. So if you really want to have your head kind of have some issues, you're right, why? I can, So in order to make this calculation, one of the things we're going to have to do is put all those pieces together. We need to take a look at what we're going to use for the size of our piece of wire, how big the current is, the cross product with R, and how far away from the wire it is. We know that this part is going to be, a constant. It will come out in front of our integration. But when we do this, one of the things we're going to have to kind of determine before we even get started is how we want to add up all the pieces of the wire. One of the things we could do is we could say that this length represents S, the distance along the wire to where DS is. Because remember, we have to find a way to point at our piece of wire from the location where we're trying to find the magnetic field. This would allow us to be able to run our integration. We could run it from negative infinity to positive infinity. Or we don't have to use S at all. We could consider theta could be used to determine this. But theta's a little harder. If we use theta for this, just a reminder, we'd have to run this from 0 degrees, which is effectively at negative infinity, all the way to 180 degrees, which is effectively at positive infinity. We have choices. Probably could run it from 0 to negative infinity or 0 to positive infinity and double our answer at the end. All these are fine choices. You know that I tend to like the latter, because it protects us in case we get into one of those traps, those trig traps. But let's see how we can set this up. We have options is what I want to point out. We have options. So the next thing I want to do in setting up this integral is I want to put in place everything that we know about this and use the letters that we have. There's not much to do here, except I'm going to pull out the mu over 4 pi, which we now know pretty crazy. I is a constant too, so I'm going to pull the current out. Doesn't change. And then inside our integral, we will have sine theta ds over r squared. Now here's the deal. That will equal the magnetic field, assuming we run this from negative infinity to positive infinity. Let's put all the pieces in place. Any question about where any of those pieces came from? Yep.
What happened to your R hat?
When I took the cross product, the r hat is a unit vector, so it's the size of 1. So ultimately what actually happened, and this is not a bad thing to ask, remember, ds cross r hat should actually be 3 things. ds, vector taken away, r, which is a value of 1, it's a unit vector, times the sine of the angle between ds and r.
So
That's the cross product.
So all unit vectors are going to be 1?
That's a unit.
Okay.
The word unit here doesn't mean meters. It means 1 unit long. Does that make sense? I'm sorry, I didn't want to confuse anybody. Maybe you didn't know that from the beginning. A unit vector is 1 unit long in whatever units you're using. It brings direction. It doesn't bring size. Does everybody understand? So if ds was in meters, then it'd be 1 meter long. If ds is in feet, it'd be 1 foot long. It's just there to bring this angle to the problem. Okay, so now that we've got that, we need to realize something that might not be obvious to you guys. Oops. S depends on theta and R. R depends on theta and S. And theta depends on R and S. We need to pick one. It either needs to all be in terms of R, all be in terms of S, or all be in terms of theta. Doesn't matter which one we choose, we have to pick one. Now, you probably understand that we've done this before, but it's been a really long time. So how about I give us some suggestion here since it's been a while, but the next time I'm going to seek suggestions from you guys, okay? Here's my suggestion for the first time running at this. It's not the easiest, but it's not so hard to do. I say we put everything in terms of S, since S is already our integral vector. If we do it that way, sine of theta is r over little r, but little r is the square root of s squared plus capital R squared by Pythagoras. So we can write the sine of theta as r over the square root of s squared plus capital R squared. If we make these two substitutions, everything in that integral now will be in terms of s and capital R. And since capital R is a constant, we're okay. You guys okay with that? All right, so that's going to be the substitution. We could just have easily done it the other way. Just as easily. I think it would have been harder to put it in terms of little r. I think that would have been impossible. But I think putting it in these terms is easy. Well, easier. Now, I am kind of hoping that seeing this doesn't scare you as bad as it used to back in, September. My integral symbol, I think what I'm going to get is capital R over s squared plus capital R squared to the 3/2 power ds. Pretty confident that's what we get. You want to check and make sure? Good to go? Or ask your questions now. Karen? Yeah?
Wouldn't it cancel out?
Wouldn't what cancel out?
The square root with the square. Can you plug in the s squared plus r squared in the bottom?
So I would have, let's write that out just to make sure. Maybe Mr. Shelton's coffee hasn't kicked in all the way. It is only cup 3. Gonna burn a hole right through my stomach. So r squared would be s squared plus r squared. So this represents r squared right here. Sine theta would be capital R over the square root of s squared plus r squared. Right? That's sine of theta. And then I have ds. Isn't that 3/2 then at the bottom?
Yeah.
Oh, so you should be.
She's making sure you do.
Well, I didn't have as much of a chance to review my notes this morning as I would have liked, but I reviewed them yesterday. And unfortunately, I try not to make mistakes, but I'm human here, and I always try to talk it out when we're working together, hoping that you guys are kind of doing something similar. Now you'll notice I left off our limits. I'm going to go ahead and double and go from 0 to infinity. All right, well, this is all you guys. I don't want to do it. It looks hard. But you guys have done your calculus.
So have you.
No, I have. I've had calculus in 30 years.
You've had 30 years of experience with it.
I love that. But no, I think this is actually a very hard integral to do. And I want you to try it so you can prove me right. Look, I'm not trying to be a jerk. Now, that was a lot. Do I need to step back through that again? Are we okay? I'm looking at the confused faces. How are we doing back there in the back table? We okay? How are we doing up here in the front table? All right, how are we doing in the middle tables? What's wrong, Jake?
It's fine.
Is it hurting?
Slightly.
Look, this kind of conversion stuff is not easy to pick up. You don't get this in it's funny, you don't do this in your calculus class, but this is what's necessary. You will eventually do it in calculus. I would assume you've already done some of this before.
Yeah.
Transposition of your integrand, but I want to point out, this looks simpler. It is not. Do you know how to integrate sine squared? I don't know how to integrate sine squared. Start your U sub, you're going to find out you're just as screwed as you were before. If you don't believe me, did you try something? Do you have something in your bag of tricks? Did you already start your little 1 minus cosine squared garbage to see if that'll work? Yeah, I'm sure. It doesn't, does it? And look, we know the answer. The answer to this one has to be 1. Has to be. This must become 1. If you put it in your calculator, you'll get 1.
You can.
Yeah, you can, right? Your calculator does integrals.
Definite.
You got your limits.
Or you could just do sine squared pi. Should be in radians or degrees.
Well, it could
Radians.
be 90 to 180.
Yeah. This one, because you have the sign. You guys do understand though that this represents the most fundamental of questions, the most basic, and this is going to answer the question: why is it that magnets that I buy in a store have magnetic fields, but don't have any clear moving charges? The answer is they must have some moving charges. The current loop is the most straightforward and basic way of making a magnetic field. A loop of current is exactly what it sounds like, a single loop of endless current. They don't really exist, but you can make coils of wire, and those coils effectively are loops of current. So imagine a wire coming in and a wire coming out, but a loop in the middle. What you have inside here is your current loop. Let's take a few more minutes to talk about the loop of charge, just so that we can kind of put the Biot Savarte law to rest a bit and have an understanding of what your expectations are. Because after this, I have to talk about the contrite little problems they give that tend to support Biot Savarte. They are not fun and they're not indicative of real life, but they are very commonplace. So I think we'll need to take a few moments and see them. But just as a brief reminder of where we were, when you look at the idea of the current loop, we're looking only at the magnetic field at a single point in space. And I think you can all kind of agree with me as to why we're not looking anywhere else. You know, the magnetic field here is going to be from the contribution of every piece of wire all the way around this loop. And there's quite a few pieces of wire, but every single piece of wire is the same distance, r, away from the center of the loop. So the kind of the takeaway here, and an important takeaway at that, is that we're only finding the magnetic field at the dead center of the loop. We couldn't find it for a point over here, not easily, since every single point from the wire is a different distance away. There's a little bit of symmetry, but could you imagine trying to come up with a relationship between R and where you are on the loop? I think that'd be pretty darn challenging. But also, part of the reason we study it this way is because we're not really concerned with the single loop. We're going to be concerned with a lot of loops together. We're going to build solenoids out of this, or the concept of a solenoid. And a solenoid gets around this problem by finding a way to try and, what's the best word? I guess the best word is it tries to find a way to columnize the magnetic field and reinforce it inside the loop. And we'll take a look at a solenoid, probably maybe even today if we can finish all this in just a few minutes. So building the Biot Savarte law, and as I watch you guys, I want you to be very clear here. This is an expectation of mine, that you be able to use Biot Savarte and demonstrate where the magnetic field inside a single current loop comes from. Now, the law itself is, as we've talked, not particularly easy to deduce, but it's not terrible either. It has all the structures that we've come to expect when we compare it to electric fields. Our goal is to try and build an integral in such a way that we can take the integral for the length. And that's what we tried to do yesterday with the infinitely long wire, so we're going to continue to try and do here today. Now, when I look at this law, in this example, all of this is a constant. It will be the same everywhere around this loop. So the only thing that I'm really interested in kind of deducing is how this is affected by the particulars of my geometry. But everywhere in the loop, the current's going to be the same, and when I'm looking at this point in the center, R is the same. So the first thing I would do is group all that stuff together. Oops. And now we have ds cross r hat, I mean. ds cross r hat is the thing that we kind of have to work out. This is the vector cross product portion, which I would normally replace with ds sine theta. But I need to kind of qualify what this theta is and see if it has anything that's related to where I am around the circle. And this is where I was going pretty fast yesterday. But just a reminder, ds is in the direction of the loop, so it is tangent to the loop. Although I drew it in the wrong direction based on the arrows for my current. So allow me a single mistake today and draw it that way. There, that's the direction of ds. R hat has to point towards the center. Just a brief reminder, R is in the direction from the current loop to our point our point of application, or our point where we're interested. So I don't think it's a big stretch for us to look at that and say that every single place in the current loop is going to provide an angle of 90 degrees between ds and the center. So that immediately changes my integrand into this. If I want the magnetic field, I just have to sum up over the whole loop. Now, technically, I always like you to consider that we could replace ds as r d theta and go around the loop in an, based on the angle from 0 to 2 pi. But there's no actual difference between a piece of current here or a piece of current there. So it is just a length. So there's nothing wrong with saying I'm going to integrate this over the circumference. Yes, sir?
So the current is a constant in this example?
Yeah. So this gives me mu naught I over 4 pi r squared times 2 pi r, which gives the result that we had yesterday, but I kind of blew through it pretty fast. Mu naught I over 2r. A current loop. Any question about that? Pretty straightforward. The current loop is the basic construct for creating a uniform magnetic field. This single current loop does not have a uniform magnetic field, but it's the basic construct for it. Putting current loops together is how we collimate the field and turn it into a uniform field. But this particular example isn't like that at all. Only at the very center is that the reading for the magnetic field. Everywhere else, the magnetic field is going to be something less and points in some other direction. Well, it doesn't point in another direction. In the plane of this loop, the magnetic field is always into the page. You can check that out by using your right-hand rule. And in the plane of this loop, outside is always out of the page or out of the board. That's also true. But if I turn the loop a little bit sideways, so that my loop has kind of this look to it, and let's say this part's in the foreground and this part's in the background. I mean, just looking at this, the magnetic field through the center goes that way through the center. But that means that all around the wire, I've got these little little magnetic fields that are wrapping around the wire, all the way around it. So the magnetic field is complex around a current loop. But there are a couple of unique features here. First, the single current loop is considered a simple dipole, and that all current loops have a field that passes through them like a standard dipole, with a, for better or worse, discussion, a pole here and a pole here. Interesting question. How do we name north and south? Interesting. You guys don't know? I figured this would be covered like in middle school. How about this? Just for fun, I'm just interested in your... So when I come back here, that means this would be considered south and this would be considered north. Now, it's largely neither here nor there. I will not be using south or north because, as you probably have come to grips with, the magnetic field is a circle and has no actual pole. It acts like a dipole in that there is a concentrated bit of magnetic field in the center of this loop. And this loop will attempt to align itself with other magnetic fields. And we actually say that there are no monopoles in the magnetic field. But what we're ultimately saying is there are no dipoles either. The magnetic field loops are circular and complete and don't break. So all magnetic field lines have no point of origin and no point of termination. They are a circle. Now, I know that that's a little weird, but let me at least address something that I really think is ridiculous, but they put these in your problems all the time. And it behooves me to have to show you this. Close enough. Let's assume I have a current carrying wire that has a half circle bend in it of radius r, and that the current goes from negative infinity to positive infinity. And I'd like to determine the magnetic field here, current I, radius R. Please take a moment and see at your tables if you guys can figure out what the magnetic field is at point P, the center of the loop portion of the wire. Gary.
Our hat would have an angle of 0 or 180.
All right, let's just do that. If I choose a piece of the wire right here, the current is in this direction. That would be our DS. And at the same time, what direction is R hat? Wouldn't R hat also have to point in this direction? So what is our angle between DS and R hat? What is the sign of 0? So these wires that point at the point, they don't contribute to the magnetic field. And we kind of already knew that a while ago when we were talking about the velocity of a particle and it moving towards a point wouldn't have a magnetic field in front of that particle. So the approaching particle doesn't produce a magnetic field in front of it, only to the side of it. The same with the current. A current doesn't produce a magnetic field in front of it or behind it, just to the side of it. So although there is a magnetic field around this wire, like this, there's no magnetic field in front of it. So the only part that contributes to the magnetic field is the curved portion. It's half a loop, so it's going to be mu naught I over pi r. In this case, capital R. So they do all of these ridiculous problems with a section of a loop that looks just like this, with the current coming in, pointed right at the point that we're interested in, and then the current going out either along the same line or, in the case of this one, going, continuing in the direction it had. So you'll see something that looks like this. You'll see problems that look like. Let me draw this a little bit neater, or try to. Something like that, where the point's here, so only this portion of the curve and this portion of the curve actually contribute. The difference is that this magnetic field is into the page and this magnetic field is out of the page. But this piece of wire has no contribution to the magnetic field since it points at the point in question. And neither do these two have any contribution to the magnetic field because they point away or towards that point. So they'll create some weird geometries like this to see if they can catch you. Don't be caught. However, and this is where we need to be more cognizant because this is more the real world. You can't see the red ones. There's every reason to believe they could produce one like this, where a single wire is bent into a complete loop. So the current might be doing something like this. Can you imagine this one? This one's not so tough. Try it out. It has the obvious answer you are thinking. See if you can come up with what that obvious answer is. I want the magnetic field at the center. All right, I'm impressed. Ricardo has it. Let's hear it.
I think we just add the two in the line of current.
All you have to, the magnetic field is a vector. So first, ask yourself, is the component from the wire and the component from the loop in the same direction at the point in question? You should check that first. And I'm noticing if I look at just the wire contributes a magnetic field that is into the board. Now I'm going to look at the loop. Does the loop also contribute to a magnetic field that is into the board? Yeah, you just add them together. So the total magnetic field, what's the contribution from the wire? I'm waiting. Sorry to bore you, Sabri. That's okay. Can you tell me the contribution to the magnetic field from the wire?
It's U naught I with 2 pi r.
Great. And can somebody else tell me the contribution from the loop? Which we just did. So look at your paper and tell me what you wrote down. Yes, sir.
mu naught I over 4.
Yeah. Now look, we've looked at all of it now. There's really not that much to go here, is there? Yes, ma'am.
Is it the same capital R for both of them?
It would be the same because it's the same distance from the wire to here. So yeah. So you'll find your book is filled with these kinds of examples. The magnetic field from a current carrying wire, all with slightly different geometries, slightly different bending of the wire. I will assign a few that I think you should look at. This is not predominantly what's on the exam, but understanding the current loop is important. Is there any question about this yet? Okay. We need to understand this. The idea that a current loop produces this magnetic dipole moment, a bit of a magnetic field through the center of the loop. The reason, I hope, is obvious. We can steer that loop, meaning we can turn the loop with an external magnetic field. So if I have something that creates a permanent magnetic field, then I can make a wire loop align itself with that magnetic field. This is the basis of producing a motor. And that's where we're going to go, is to talk about how motors work. Now, to get an understanding of a motor, you need to be able to understand where the force is on the motor and how the motor is going to work. So to understand that, I want to kind of help produce something. There's a few things that we have to see before I do. But the first is we need to talk about placing these wire loops now inside an external magnetic field. To make it easy on you, the wire loop I'm going to choose to use is square. So that's my wire loop. It's square-ish, kind of. It's square. And we're going to say that we're going to immerse this wire loop in a magnetic field that points into the page. Into the page is completely useless. Mr. Shelton should have been thinking more. Did you already draw all those X's?
Yes. In pen.
In pen?
Yeah.
All right, well, this will not let our motor turn. That's okay. Let's make sure we know why. Mr. Shelton was thinking of a future question while he was drawing this, and he should have been more proactive. But if that's the direction of my current, right-hand rule this and figure out why Mr. Shelton screwed up. Take a moment. Find the force on each piece of wire, please. I would say that you have 5 pieces of wire to work from. Don't worry about the 2 lead-in wires that go to the loop. I intend to ask each of you about section A, B, C, D, and E. You're going to tell me up, down, left, or right. So, are we ready? Adam, what direction is the force on wire segment A? I don't think so. Let's try again. Current's that way. Rotate my finger to point in the direction of the magnetic field. Down. There we go. That would be the force. All right. So Luke, B. Yeah. Chris, C. Matt, D. Julie E.
Down.
Yeah. That's probably not going to do a whole heck of a lot to my wire loop. So perhaps Mr. Shelton should change the orientation of the magnetic field. So that's what we'll do. We will back out of this and try again, Mr. Shelton. Be a better teacher. Be the teacher these kids really deserve. So let's try a magnetic field that is directed this way. Yes, this way. This is the way. There we go. Current still going the same direction. It's traveling more or less counterclockwise through this loop. Now we have the potential for what I'd like. Take a moment and do the same thing. A, B, C, and D it. Be prepared for me to call you out. You've got, I don't know, I'll go with 10 seconds. You haven't drawn the picture? A. A is up? No. Current's that way. There's no way to rotate my finger to line up with the magnetic field because it is that way, which means nothing. Zero magnetic field there. In fact, there's probably more places with zero magnetic field. Anybody want to shout out one of them? Another one? There we go. No magnetic field force on any of those portions of the loop. All right? However, that leaves B and D. Zach, give me B.
Out of the board.
Who agrees with Zach? Excellent.
What do you got, Zach?
How about D? Into the board. So now you see how the force is going to affect this. Hey, folks, do me a favor, real quick. What is the direction of the magnetic field created by the loop? The magnetic field created by the loop. So out of the board, magnetic field created by the loop. And what direction is this loop being turned due to this external magnetic field? Do you realize that it's being turned? If this is the loop, it's being turned like this, so that if the magnetic field is coming out, it's being turned to line up with the external magnetic field. Do you see that? That's important for tomorrow's activity. Your exceptional knowledge. So let's see for a moment. Here's the Earth. And if we assume the north pole of the Earth, is that the direction of the magnetic field? What part of a magnet gets aligned towards the north when we hold it near the surface of the Earth? Does anybody know? All right. The north pole of a magnet points towards the north pole of the Earth. Now, this part's important because I want to try and explain this to you as best I can. If I have a small bar magnet and I hold it near the surface of the Earth, the north side of the magnet will point towards the north side of the Earth. Thus, we've labeled magnets based on lodestones, the original chunks of iron pulled from the Earth that sailors used to notice would line up towards the north. In order for that to be the case, the magnetic field lines here have to be running in this direction. Wait for it. That means if I was to continue those field lines, they don't pass that way through the earth. They pass this way through the center of the earth. The north pole of a magnet points towards the south pole of another magnet. Does everybody understand? Did you follow that argument? Suggesting that the actual dipole of the earth has a magnetic field in this direction through its center. And that would mean that the south side of the magnetic field is at the north pole of the earth. Thus, north magnets point that way. You can follow that argument a little bit, can't you?